Welcome, all of you. Today, we will discuss the space Bxy and Cxy. Bxy is the set of all bounded functions from x to y, and Cxy is the set of all continuous functions from x to y. We have already seen that CAB, the closed interval AB. So, we have seen that closed interval CAB. Okay, CAB is the set of all real valued continuous functions from the closed interval AB. That is, if you have f a function on CAB, it means that f is a function from AB to R and it is continuous. Okay. Now, the question is that, so this is the space of all continuous. So, if I replace this closed interval by a metric space X and this by a metric space Y. So, then we will have like this C X Y. So, C X Y is the set of all continuous functions from a metric space X to another metric space Y. And similarly, for B is a set of all Bxy is the set of all bounded functions from a metric space X to a metric space Y. So, here is first let us introduce a definition of a bounded function. Okay, bounded function, you see, as again you have seen that if you have a function f from a metric space X to R, then you can say that the function f is bounded if there exists if for every there exists a constant m such that f of x mod is less than or equal to m for all x is in x. Okay, so this is the definition of the bounded function. But again, here if you have this, you replace by a metric space y, then you see this would not be a mod of x. The y must be an element of capital Y. So how we can write this? So how we can say that the function f is bounded from a metric space x to a metric space y? Because there is no way to replace mod of f of x by some kind of things related to the y. So here is we can do it that if the function f from a metric space, so we can see that if you have a function f from a metric space x to a metric space y, then we say that this function is bounded if f of x, which is a subset of y, is bounded. And this is a subset. Let us call this set is say for example d of some d. So, okay. Then the set d is bounded in this one. It means what? It means that the diameter of this is finite. Or you can say that the diameter of this, it means that if you take y1, y2, any two element in f of x such that the metric dy, y1, y2, okay, if there exists a constant m such that this distance is less than or equal to m for all x, y1, y2 in f of x, then we say that the function is bounded from a metric space x to a metric space y. So, this way we define the boundedness of a function from a metric space x to a metric space y. Similarly, and also we will see that the space Cxy set of all continuous functions from a metric space x to another metric space y. So, let us take here is we take x dx, this is a metric space with respect to the metric D, and this y is a metric space with respect to this metric. So a function f from a metric space x to a metric space y is said to be bounded if f of x, if this set okay, is bounded in y. This set is bounded in y means that there exists a constant m, okay, such that d y1, y2, the distance for any 2 pointer, any 2 element in f of x, the distance between any 2 element of f of x is less than or equal to m. And so set of all bounded functions is denoted by bxy. Now, remark, every continuous function defined on a compact set, every continuous function defined on a compact set is bounded. Why it is so? Because suppose x is compact, okay, and f is continuous from x to y. Then we have seen that if x is compact, then f of x is a compact subset of y. Okay, so f is a compact subset of y, and every compact subset of y is closed and bounded, and therefore f of x is bounded, and so the function f is bounded. So the first example is that every continuous function defined on a compact set is bounded. Now we have an exercise. Okay, so exercise says that if fn is a sequence of bounded functions defined on a metric space x to a metric space y, and f is a function from x to y, okay, and if fn converges uniformly to f on x, okay, then f is bounded. Okay, it means that you have a sequence fn of bounded functions, and this sequence fn converges to the function f, converges uniformly to the function f, then the limit function is also bounded, as we have proved in for the continuous function, that if you have a sequence of continuous functions defined on a compact set and converges uniformly to f, then f is continuous. So same as here is f is bounded. This proof is very simple, because fn converges uniformly to f, so by the definition there exists a positive integer n such that d f, y and x, f of x is less than or equal to 1 for all x in n and all n is greater than 0. Now fn is bounded, so there exists y and m such that this distance is less than m. Now we can see that d f x y is less than or equal to this plus this one, and this is less than m, this is less than 1, so this term is less than m plus 1. So we have taken any y in f of x, so you can treat this y is equal to, so corresponding to this y we will get some x, one say in x, and such that f of x1 is equal to y, so the distance between x, f of x and f of y is less than with some constant, and therefore the function is bounded. So this way we can prove that the limit of the uniform convergence bounded sequence is bounded. Now let us define a metric on the space bxy. Bxy, set of all bounded functions from a metric space x to a metric space y. So let x and y be two metric spaces, and rho is a map from x to y defined in this way. That is to say, rho fg is equal to supremum of d f of x g of x, and taking the supremum over x in x for all fg in bxy. And then very easily we can prove that this rho is a metric on bxy, and bxy, this metric rho is a metric space. Now there are two things. This is a metric space. So let's say okay, here is let X and Y metric space Fn be a sequence of functions in Bxy. So Fn is a sequence of functions from X to Y. Now Xn, then Xn converges to F as a sequence. Okay, as a sequence. Okay, because this is a metric space. So Fn is a sequence in this metric space. So when we say that this sequence converges to X, it converges in the usual sense as we have seen earlier. Because here is only here the Bxy is a metric. So the sequence Fn converges to F means that it is the convergence in the metric space. Okay, so when Fn, then Fn converges to F, okay, with respect to the metric row. Okay, so in other words, you can say Fn converges to F in the usual sense, in the sense of the metric space. If and only if Fn converges uniformly to X. So if it is converges with respect to the metric S, then Fn converges uniformly to F. So in other words, you can say that the uniform convergence of the sequences in Bxy converges to F is equivalent to say that the convergence with respect to the metric row. So let's prove. So to prove this one, let epsilon is greater than 0 and assume that Fn converges to F, A, and F is an element of Bxy with respect to the metric row. Then by the definition of the convergence, okay, we have there exists a positive integer n such that rho Fn F is less than epsilon for all n is greater than n. And so for n is greater than n, we can say that here is a supremum of rho Fn x is less than epsilon. But this is rho Fn is what? This is equal to this term from the definition. So it is equal to this, and this is because this is the supremum of this one. So this supremum is greater than with this one. And therefore, d Fn x f of x is less than epsilon for all x. So this is true for all x. It means that Fn converges uniformly to F. Now for the converse, assume that let epsilon greater than 0 and suppose that Fn converges uniformly to F. Then we will have to prove that it converges to F, to a bounded function F from X to Y. So by the definition of the uniform convergence, there exists a positive integer n such that d Fn x f of x is less than epsilon by 2 for all x in X and all n is greater than 0. Now for n is greater than 0, what we can have? We can take the supremum. Here is we can take the supremum over x in X. If we take the supremum over x in X, then this term, so here if we have this supremum over x, then this is equal to, by the definition, is rho f of g. So this is equal to rho f n x. But this is what? This is this is less than epsilon by 2. So the supremum of this less than or equal to epsilon by 2. But epsilon by 2 is always less than epsilon. So this is less than epsilon for all x. It means that f of n converges to a bounded function from x to y with respect to the metric row. So this way we can prove that the uniform convergence of functions is equivalent to the ordinary convergence with respect to the metric on Bxy. Now we define a metric on Cxy. So let x1, y be metric spaces and Cxy is the set of all continuous functions from x to y. Okay, we further assume that x is compact. Now here is we assume that x is compact. Then we define a function or a mapping rho from Cxy cross Cxy to the to R plus or close interval 0 infinity by a rho fg is equal to supremum of d f of x gx, and supremum is taken over x is in x for all fg in Cxy. Now, the thing is that we are considering that the x is your metric space. Okay, so x is metric space. Then first we have to we will show that this row is nothing but it is the metric on Cxy. So to prove this mapping okay is a metric on Cxy, we establish first the following lemma. What is the lemma? Lemma says that if x and y be metric spaces and x is compact, okay, then for any fg continuous functions from x to y, rho fg is equal to supremum of d fx gy, and supremum is taken over x. This is finite. This is finite. So, and there is an element x such that this is equal to, so it means that is equal to rho f of g. In other words, we can say that the supremum exists and which is equal to rho of x. So, because we have to prove that if we can say that it is if we prove that the function hx, okay, hx is equal to d fx gx. If this function is continuous, okay, and this function is continuous means the function h is continuous on x, and x we are considering is a compact space, and we have proved that every continuous function defined on a compact set has a infimum and supremum. So the supremum will exist, and then there will exist a point x such that this must be equal to rho f of g. So this will be holds good, and of course because the infimum and supremum exists, so this value this must be less than or equal to the supremum of this one and is greater than or equal to the infimum of this one. So it is finite, and therefore we get that this is a finite number. So let's take here is then by extreme value theorem the result follows. Okay, so if we prove that this h is continuous, then by extreme value theorem, which is we have mentioned as the exercise 5.3.4, the result will follow. So by the triangular inequality, we have d fx gx is less than or equal to d fx fy plus d fy gy plus this thing. Now we can take here is this is the same as one, and this term you can take on the other side, and then we have this one. And now this is all that now we can interchange x and y. So here is here we can put y, and here we can put y, here we can put x, and here we can put x, here we can put y. Okay, so this will be f of y, and then here we go put, so it will go. And now because we can use the symmetry, so we can write again in this way, and same is here. We will get g of x here. So we change symmetry property, so we can write a g of x is here and g of y is here, so we can write here. So then we will have this one. Now this means what? It means that this is what? This is your h of x, and this is your h of y, and this is your h of x. So mod of h of x of y is equal to mod of this one, but this mod of this is less than or equal to this plus this, and okay, this plus this one. Now since f and g are continuous, so for given epsilon positive there exists a delta positive such that d fx fy is less than epsilon y2, and similarly d fg fgy is less than epsilon by2. So this is less than epsilon by2, this is less than epsilon by2, so whole this is less than epsilon. So this is less than epsilon whenever we have dxy is less than delta. So this is because this is whenever this is less than delta, and therefore h is continuous. So h is continuous, and we get the result. So now we are ready to prove that the row which we have defined in this way is a metric on Cxy. So of course we will assume that X is your compact space. So as we have seen in the previous lemma, that rho Fg is greater than or equal to 0 for all f and g, and other properties of the metric can be easily checked. The only thing is that we will have to check whether the triangle inequality holds good or not. So for that, let f, g, h are three elements of Cxy. Then by previous lemma, there is a point x in x such that rho Fg is equal to this one. But then the rho Fg is equal to d f of x, g of x, and this is less than or equal to this by using the triangle inequality. And this is what? This is your rho Fh and this is your rho Hg. So rho Fg is less than or equal to rho Fh plus rho Hf, and so it satisfies all the properties, and then we can see that this is a metric on Cxy provided that X is a compact metric space. But as we have seen before that here is we can define a metric on Bxy. In the same way, rho Fg is equal to supremum of this one. So, but here is X may not be bounded. So, in the same way as for the bounded set, we can define the metric for the continuous functions from x to y the same, but here the X must be compact. Okay, so this we have proved that the metric defined in this way is a metric on Cxy with X is compact. Not only this, if X is your compact metric space and Y is complete, okay, here is we have Cxy and rho is this metric on Cxy, okay, then Cxy rho is a metric space, and now this is a metric space provided that this X must be compact. Now if Y is complete, then this metric space is a complete metric space. So this metric space is complete. Okay, let us take so we have already proved that this is a metric. Here is we have proved that this is a metric. We have to prove that it is complete. That is to say, we have for every Cauchy sequence is convergent. So let us take Fn be a Cauchy sequence in the metric space, this one. Okay, and take X be any fixed element. Now, since dFnx Fmx is less than or equal to rho Fn Fmf. Why it is so? Because from the definition of the rho. Because the rho Fg is less than or equal to, because this is equal to the supremum of this one. Okay. So it means that this is the supremum of all these elements. So it means that this is greater than or equal to with this one. So here is this is greater than or equal to. And the function values, and therefore you can see that this function value, because this rho Fn Fm, okay. So since this the function value f of x, so it means that this is a this is a Cauchy sequence in a complete metric space Y, and therefore Fn x converges to some point f of x in Y. This means that Fn converges pointwise to a point f. Now we prove that this point f is also lies in Cxy. That is to say, f is a continuous function from x to y. Okay. So and that Fn converges to F with respect to the metric F. So, since Fn is a Cauchy sequence for any epsilon positive, there exists a positive integer n such that this is whole square. Rho Fn Fm is less than epsilon by 2 whenever Mn is greater than 0. And now, and because this is a Cauchy sequence, this is holds good for all. This is holds good, and that is for all x and all nm greater than n, d f n x fm x is less than epsilon by 2. Now take m tends to infinity. So when take m, then for all x and n is greater than 0, we can take here is we are taking the m converges to m tends to infinity. So this, because this function is continuous function, so you can take it is inside, and this converges to f of x. Okay, so we can write in this way. But this is what? This is less than or equal to epsilon by 2, but it is less than epsilon. So hence Fn converges uniformly to F. And now by the theorem 5.6.1, F is uniform continuous and belongs to Cxy. Finally, the previous proposition, from the previous proposition, we can say that Fn converges to F in this metric space. Okay. Now, the following proposition shows that the convergence in Cxy is exactly same as uniform convergence, as we have seen in case of bounded space of bounded functions from a metric space X to a metric space Y. So here is we have X and Y are metric spaces. Again, X is your compact, and Fn be a sequence of functions in the metric space Cxy rho. Then Fn converges to F with respect to the metric this if and only if it converges uniformly to F. Now, here is the same results the holds good for the bounded sequence, but in the bounded sequence we are not the X may not be compact, but here is if X is compact, then we have this kind of the result. Now, from the proposition 5.6.6, we can say that Fn converges uniformly to F if and only if this converges to 0 as n tends to infinity. And this converges to 0 at tends to infinity means what? It means that rho Fn F converges to 0, which means that Fn converges to F in C with converges to F with respect to the metric rho. So the proof is very simple.